We have studied oscillations and vibrations in great detail. Now we will expand our analysis. Now changes in physics, that is dynamics, is basically of two types. We have already covered one type and is related to particles and consequently combination of particles. So particles are localized entities, which means you can assign specific coordinates to them. But dynamics is not just for particles. We can have one more kind, which is known as waves. Waves are entities which do not localize at a certain point but spread out through space. There are many ways of looking at waves. One way is to think of it as a traveling oscillation. So imagine a particle oscillating in a simple harmonic motion. Now imagine this particle moves in a certain direction. Then that would be considered a wave. Another quite subtle way of looking at waves is to think of it as an infinite number of oscillators which are coupled to each other. We are going to look at these interpretations. For now you can think of waves as anything which goes through space with some speed and spreads out. So let's make some clear distinction between particles and waves. So particle is simply a point mass. So particle is simply a combination of point masses, which means you can assign them specific coordinates. So this gives rise to the concept of a position vector for a particle where it might be situated. Another important feature of a particle is that at any point in space only a single particle can be present. So if you have a particle, let's say at the position 1, 1, then no other particle can be simultaneously in that position. So you cannot add particles like that because particles occupy space. So a good mathematical way of thinking about a particle is to think about a discrete function, a function which takes only specific values at points. Wave, on the other hand, is not localized at a single point but can be present at multiple points. So think of this as a continuous function in space. Secondly, two waves can be present at the same point. So you can imagine two water waves which are coming at a certain point, then they both exist at a single point. This is the principle of superposition, which we are going to deal with later. It's an important defining feature of a wave. But if instead of these waves we had particles, what would happen is they would collide with each other and then go in a separate direction. But two of them cannot be at the same place. So the way to write it is that waves can superimpose. The second statement is not to be taken lightly. This property is one of the most important principles of physics, and it gives rise to a variety of phenomena like interference, diffraction, polarization. This is also a major effect in quantum physics. So as we'll see quite later, even atoms, electrons, protons and fundamental particles behave like waves and superimpose. The connection between waves and particles is quite subtle and is one of the integral properties of reality. So there should be a motivation for studying waves. Practical examples of waves abound all around you. For example, you have water waves, waves on a string, light waves, sound waves, and even quantum waves. Waves are just a different way of transporting energy than particles, and hence we are going to explore this in quite some detail. So in the coming series of lessons, we are going to study two kinds of waves, namely transverse and longitudinal waves. Particularly we'll be focusing on sound waves and waves on a string. Then in a later lesson we'll focus on the other kinds of waves, which are electromagnetic waves and light. So now let's look at waves as an extension of oscillations, particularly a simple harmonic oscillation. So the best way to look at it is using a string. So imagine you have a string and the string is tied at one end, and you are holding the string from the other end and you give it a jerk vertically like this. So the information that this end of the string has been extended is relayed along this string. So as far as this point is concerned, this is only doing a translational motion. It has gone up. It can also come down with your hand and then it will be an oscillation. But the part of the string which is next to it will also experience the same pulling motion and hence will respond to it. When this responds and starts going up, the part which is next to it will also respond to this motion and will start going up. then the cycle will continue and the entire information passes through. This is precisely a wave. It is a disturbance which travels through this medium. And what is the disturbance? The disturbance is simply the displacement of these points of the waves upwards and downwards. If you are oscillating it, then each part of the wave will oscillate upwards and downwards. So how will the string look? So this is how the string looks at t equals to 0, at which point you start to pull this end up. As a result, the string will now start looking like this. Soon different parts of the string start responding and the string will keep on extending like this. Now if you want, you can bring your hand down. Consequently, this part of the string will respond to it and the wave will start looking something like this. After some time, the disturbance comes back to its mean position and the wave has traveled all the way till the other point. So you can see how the disturbance which was created at one end travels to the other end. Each point on this string starts to oscillate. First this point oscillates, then this point, and so on. So there are infinite number of points on this string which will oscillate. This is precisely the reason why I mentioned before that a wave can be thought of as an infinite number of coupled oscillators. Coupled because each of them are connected to each other. They are not independent. They are going in a synchronized manner. So after the wave reaches this point, then the wave starts to return back and then the whole motion follows in the opposite direction. Now of course, in general, the oscillation which is driving this wave can be anything. It need not be a simple harmonic motion. It can be a motion with a constant speed as well. It's all up to you. Depending on how you move it, the wave will also look differently. So this particular wave is an example of a transverse wave. A transverse wave is one in which the disturbance is in a direction perpendicular to the direction of motion, exactly as the case over here. So the motion or the disturbance is in the vertically upward or downward direction. Let's call this direction as the y-axis. But the wave itself moves in a different direction. It's moving horizontally, which would be the x-axis. You can contrast this to a different kind of wave known as a longitudinal wave. In a longitudinal wave, the disturbance travels in the same direction as the wave. So if the wave is traveling in the x direction, it oscillates in the x direction as well. So the motion would be something like this. It's oscillating as well as moving. An example of this is a sound wave. In a sound wave, the individual particles of air oscillate horizontally in the same direction in which the wave travels. So some examples of transverse waves are waves on a string. Then you have waves on the surface of water. This is a perfect example of a transverse wave. The disturbance is vertically upwards and the wave travels in the radial direction like this. Also, you can notice how these two waves are superimposing at a single point. So this confirms our statement before that two waves can exist at the same point. So we have surface water waves. Then even electromagnetic waves are transverse waves. So light is an example of that. In an electromagnetic wave, the disturbance is not a displacement of any particle, rather it is an electric field or a magnetic field itself. So you have electric magnetic fields in a plane and the direction of traveling of the wave is perpendicular to that plane. An example of a longitudinal wave, as mentioned, is a sound wave. In a sound wave, the physical quantity which oscillates is the particles in the medium or the pressure at each individual point. So sound wave is also a pressure wave because the pressure is oscillating. We'll look in detail at this motion later. But now let's try to develop the mathematics of any wave. So to begin introducing the concept of a wave, first we have to look at a mathematical construct, that is a multivariable function. So till now we have only dealt with functions in one variable. So for example, your function of x. More generally, we always look at functions of the time t. But there can be a function which depends both on x, which is the position, and the time t. So then it will be f of x comma t. This is a two variable function. As a matter of fact, you can have multivariable functions like f of x, y, z and t. These will be used to represent waves. This will be a wave which goes in one dimension, and this is a general three-dimensional wave. But now if we focus our attention on plane waves, that is waves which move in a single direction like this, then we can see what kind of functions do we expect. So what exactly is this function if it represents a wave? So this function is anything which is oscillating in the case of a wave. So for a wave on a string, this function would represent its displacement. So a wave which is going like this on a string, then its displacement from the mean position, which is in the y direction, could be this function. So we can pick this point as the origin is arbitrary, and this direction as the x-axis. So we can pick the coordinate of any point here as x, y. Then this function is nothing but the displacement y as a function of the coordinate x and the time at which you are looking at it, because after some time this will change, because this is an oscillating wave. In the case of an electromagnetic wave, this function would be the electric field as a function of x and t. For the case of a sound wave, this would be the pressure at a point x, t. In the case of a water wave, this would be the displacement or the height above the water surface that the wave comes. So in general, all points on this wave oscillate and change with position as well as with time. But there are two ways to look at it more clearly. The first one is to freeze a frame, which means look at a wave and take a picture of it. So a picture of a traveling wave, for example, would look something like this, which means that the time coordinate has been fixed. So this function is at a fixed time. So you can specify at t equals to 5 seconds I took a picture, and this is how the wave looked. Now since you have fixed the value of t, y becomes a single variable function only depending on the coordinate x. You can find the equation of this curve, and that will give you the wave. Another way of looking at a wave is to fix a coordinate, which means we are only looking at a single point, but now the time changes. So forget about every other point, just look at this one and see what happens when time changes. So this particle will go up, it will reach here, then it will come down. So it simply looks like a single particle oscillating up and down. So here you have fixed the value of x. Let's say at x equals to 1 meter, I have a particle which is going up and down. This will just be an equation of an oscillation like a simple harmonic motion. So y will only be a function of t. If it was simple harmonic, it could be something like a sine omega t plus phi. So these are two ways of looking at a wave. You have multiple particles which are situated at different x coordinates, each of them oscillating like this. Now a wave is simply a disturbance which travels to the x direction with some speed v. So what is meant by the wave speed v? So imagine this is a wave. At some time t, let's say t equals to 1 second, a particle is over here. We can see its coordinate. So the wave speed simply implies that after a certain time, this whole disturbance would have shifted by some distance d, which will be equals to the wave speed into t. So after time 1 second more, that is after 2 equals to 2 seconds, the wave would have shifted to the right. So this point over here has a certain displacement y. Now the same displacement is found for a particle which is over here. What is the distance between these two particles? So this disturbance has traveled a distance which is equals to v into t. So these are two snapshots taken at two different times, t equals to 1 second and t equals to 2 seconds. So this first snapshot, let's say it's given by a function y of x comma t. This is 1 second. In general it will be, let's say, t1. So this is a snapshot at t1 and this is a snapshot at t2. The wave has traveled by a distance v of t2 minus t1. So now since the y displacement of these 2 points is the same, we can write this as yx comma t1 equals to y x plus v t2 minus t1, which is the x coordinate of this point, comma t2. Notice how it's a function of two variables. So from this equality, one thing immediately becomes clear. If the equation for y is written as a function of x minus v into t, then you can calculate it at each of these points. So for the first one, it will become y of x minus v into t1. For this part, it will become y of x plus, instead of x you put this whole thing, which is x plus v t2 minus t1, minus v into the time at that point. The time at that point is t2, so this will become minus v t2, which becomes y of x minus v t1 itself. So this becomes an equality. What this suggests is that this equation will always be satisfied if the function is of the form x minus vt. So any function which is written as x minus vt represents a wave or a disturbance which is traveling with a speed v in the direction of x. So when we are taking these snapshots over here, what we do is simply fix the value of t. So if the displacement is given as y of x minus vt, we fix t equals to whatever we like, and that gives you a single function. But what would happen if the wave were traveling in the opposite direction? So the wave is now traveling with minus v velocity. In that case, only the sign of v changes and the function will look something like this: f of x plus vt. So we can summarize this by saying any function given as x minus vt represents a forward traveling wave. And which is the forward direction? The direction in which x increases. Any function of the form x plus vt represents a backward traveling wave in the direction of minus x. Functions of two variables which do not look like this do not represent a wave traveling with a constant speed. Now we have seen that any wave is given by the equation of f x plus minus vt plus minus depending on the direction it is going. Now it might be that the speed v is not always constant for a wave, but for a small differential time we can always take the speed to be a constant. In any case, what we want is to find a differential equation that every traveling wave will satisfy. That is a differential equation that f satisfies. Now since this is a function of two independent variables, we'll have to use partial derivatives. So let's differentiate this function once partially with respect to x. So we want del f by del x. Also look at the partial derivative of f with respect to the time variable t. Now these two derivatives will look exactly the same because it will always be in the form of a linear equation like this. As an example, let's say the function is sine of x plus vt. If you differentiate partially with respect to x, which means treat this as constant, this will become cosine of x plus vt. But now if you differentiate with respect to time and treat x as constant, it will again be cosine of x plus vt. But the difference is that the chain rule causes this v to come out. So in any function, the v should come out due to the chain rule. So from this example, it becomes clear that del f by del x multiplied by plus minus v, the sign also comes out, should be equals to del f by del t, because their form is the same. This linearity should ensure that. But we can actually do better than the first derivative. We can take the second partial derivative with respect to the individual variables, which means we are looking at del square f by del x square, and over here del square f by del t square. Now when you are taking the second partial derivative, one more v will come out because of the chain rule again. So it becomes clear that you will get a plus minus v multiplied by a plus minus v over here. Plus minus will simply give you v square. So you get v square del square f by del x square equals to del square f by del t square. This is a very important equation. This is known as the wave equation. Any traveling wave will always satisfy this equation, whether it be a sound wave, light wave, wave on a string, a quantum wave, electrons, protons, everyone satisfies this equation. So if you look at the dynamics of a certain system and you find out that the equation of motion, the differential equation, looks something like this, then this would be the equation of a traveling wave, and the coefficient of the second partial derivative with respect to x will be the square of the speed of the wave. This is the way of calculating the speed of any wave. For a sound wave, this f would be the pressure, and you would get del square p by del t square equals to v sound square del square p by del x square. Here Vs will be the speed of sound in that medium. So remember, from this derivation, any function which satisfies f of x plus minus vt will satisfy the wave equation. But remember, if this wave is not traveling with a fixed speed, then you cannot use this, since the partial derivative with respect to t will also include v. Now we proceed to look at some mathematics of these partial derivatives. In general, if a wave is traveling in more than one dimension, then it is given by the equation del square f by del x square plus del square f by del y square plus del square f by del z square, the three coordinates, equals to 1 by v square del square f by del t square. This is a special operator. It's written as nabla square, also del square. This is known as the Laplacian of f. So a general three-dimensional wave is written as del square f equals to 1 by v square, partial derivative of f with respect to t square. Now this section could aptly be named as the kinematics of waves, which means we'll look at their velocities and accelerations and other derivatives without looking at the causes of those motions. We have done the same for particles, motion in one dimension, motion in 2 and 3 dimension, and then we moved on to dynamics to find out the cause of those particular motions. So right now we're going to look at a wave from two perspectives. First, we're going to look at a snapshot of it at a particular time. So at time t equals to t1, let's say a wave looks something like this. So this is again a picture of the wave, which means we have fixed t. Now this is the coordinate x, so you can fix this origin, and any point will be given as x comma y. Now this is simply a graph of a function which is drawn for a single variable. So this is like y equals to x evaluated at a fixed time. So if we calculate dy by dx for this graph, that would give us the slope of this particular line, the tangent to the curve. But now if you recall the definition of the partial derivative, if you are calculating the partial derivative with respect to one variable, you assume all other variables are constant, and this is precisely what we have done here. We have assumed t equals to constant. So the partial derivative of y x comma t with x simply means that t is equals to constant at t1, and hence this will be equal to del. So del y by del x, the partial derivative, tells you the slope of a graph at a certain time instant. Now we can also look at a second picture, which is you fix the value of x and you change time. So let's focus on this point itself. Now since we are looking at a transverse wave, the particle cannot go to the right or the left. The particle can only go up or down. So if we look at a picture with x constant, it's simply a motion up or down. We can calculate the speed of the particle itself. The speed of the particle is rate of change of its coordinate, which is dy by dt. This is v particle. So we can repeat the same argument as before, and hence this will become the partial derivative of this multivariable function with respect to t, which means assuming x is a constant for a certain value. So speed of particle at the point x1. Now I'll stress a very important point, something which can get you very confused, and that is this is the v particle, not the speed of the wave itself. The speed of the wave v tells how fast the pattern itself moves. So this whole pattern will repeat itself after a certain distance, and that is what the wave speed is telling you. V particle, on the other hand, gets the particle's velocity as it moves in a certain direction. So do not confuse these values. So to finally summarize, del y by del x gives you the slope of the tangent at a certain fixed time when you take its snapshot. Del y by del t calculates the speed of the particle at that fixed point. The speed of the wave tells how fast the pattern itself moves through x. Similarly, now we can take the second derivatives as well. So we have del y by del t is the speed. Taking its again derivative with respect to t would give us the acceleration of the particle. Indeed, the acceleration is the first derivative of the velocity. In terms of y, you have acceleration of the particle is equals to del square y by del t square. So these were the interpretation of the partial derivatives that were introduced in the wave equation. Now let's look at some solutions of the wave equation. Now we have seen this process before. When we were dealing with the simple harmonic motion, we had the differential equation, but that was a single variable differential equation, d square x by dt square equals to minus omega square x. Its solution came out to be a sine omega t plus phi. But the wave equation is much more general, and hence it has an infinite number of solutions. We are going to look at one such specific function. So assume we again have a string which is fixed at one end, and on the other side you give it a jerk such that a wave is created. But the driving force which creates this particular wave is also in the simple harmonic motion. So you can imagine a spring mass system to which you have attached this string, and as it oscillates, a wave is created by this oscillation. So this wave would go something like this. Let's find out the equation of this wave. So this would be simply y equals to f of x minus vt, where v is the speed of the wave in that string. We can also assume that the point over here is the origin 0, 0, and the y-axis is over here. So it can be seen that this wave simply follows whatever oscillation is happening on its end, because that's what our definition of a wave was. The pattern of a wave moves with a speed v. So whatever is created over here is the same which is traveling. There is also a mathematical way of looking at it. Now in this function you can take out v common, and the form of the function would be simply f of x by v minus t. For example, if it were sine of x minus vt, then it can become sine of v into x by v minus t. It should always appear in this combination. Now what we can do is we can put x equals to 0 in this equation. In that case you will get the leftmost point, which is x equals to 0. But the displacement at this point y at 0, t is known as the simple harmonic motion. That will be written as a sine omega t plus phi. So now you have a function of t given like this. Now this is at x equals to 0. As the wave travels, you can find the equation of the traveling wave as well. At x, t, you can get the result by simply replacing t by x by v minus t. So in this equation, I'll replace it, and this will become a sine omega into x by v minus t plus phi, which itself can be written as a sine omega by v x minus omega t plus phi. This is the equation of a wave which is generated by a simple harmonic motion. This is known as the sinusoidal wave. Just like in SHM, you can fix the value of the phase factor by fixing the value of time. So instead of sine, you can also have cos. How does it look when you take a snapshot? Let's say t equals to t1, we have to see how it looks. In that case, when you fix it inside, this becomes y x comma at a fixed point t1 equals to a sine omega by vx minus omega t1 plus phi. All of these are constants. This simply becomes a sine in the variable x. So the snapshot also looks like a sine function, something like this. The equation of the sine given as over here. The amplitude of the sine function remains the same as in the SHM, a. The sine function will repeat itself after moving through this distance. This is the period of this function. This is known as the wavelength, written as lambda. It is the distance after which the disturbance repeats itself. We can calculate the value of lambda quite easily from our wave equation itself. First, let's write it in a more simple form. What we are going to do is we are going to write omega by v as k. K is known as the wave number. If you know the speed of the wave and you know the angular frequency, you can calculate the value of k by this formula. Or if you know the value of omega and you know the value of k, then the wave speed is given as omega by k. So using k, the equation becomes a sine kx minus omega t plus phi. So you can see that k plays the same role in space coordinate as omega plays in time coordinate. So recall in SHM what we had done. We plotted the graph of the simple harmonic with x and t, and we found out that the time after which the sine function repeats itself was given as 2 pi by omega. In this case, when we are plotting between x and y, the distance after which the wave will repeat itself will be given by 2 pi by k. 2 pi by k is the wavelength lambda, and 2 pi by omega, as before, is the time period of this wave t. So the physical significance of each of these should become clear. If you take a snapshot of a wave, which means fix the value of time, then the wavelength tells you after how much distance does the pattern repeat itself. On the other hand, if you fix a value of x, which means you look at a single particle which is executing SHM, then t tells you after how much time does the particle repeat its motion. So it is a repetition of motion of each particle on the wave. We can recast our sinusoidal wave in terms of the time period and the wavelength. It will become a sine. K can be written as 2 pi by lambda into x minus 2 pi by time period into t plus phi, or a sine 2 pi x by lambda minus t by capital T plus phi by 2 pi. Now this factor of phi is not important, you can remove it. It simply fixes the initial point and the initial time. Up until now, whatever we discussed is true for any general wave. For a wave on a string or a transverse wave, y is given by a sine kx minus omega t plus phi. In that case, y is the displacement and a is the amplitude of that displacement. If you were talking about a sound wave, then you will get p equals to p naught sine kx minus omega t plus phi, where p is the excess pressure and p naught is the amplitude of that pressure. For an electromagnetic wave, you would get a similar equation with the variable being the electric field. But now, since we have to understand the dynamics, we are going to focus our attention only on the transverse waves on a string. Our objective is to find the speed of the wave in a string. So as before, you have a string which is fixed on one end. When you oscillate it on one end, the wave travels. Now what is the reason that this wave will travel? If this string were inextensible, then such a wave can never be generated. You can see that the total length of the string would have increased if the wave is to travel. If however it was inextensible, then however large force you apply, its length cannot change. So a key feature of any wave which travels in a medium is that the medium should be elastic, which also means there should be restoring forces which will cause this wave to subside as it travels. If there are no restoring forces, then it simply behaves like a solid block. If you pull it up, it simply remains there, does not come down. So elasticity is a necessary feature. A second necessary feature is inertia, which means that this string should have some mass. If it did not have a mass, or it had negligible mass, then it would have an infinite amplitude even with any small force applied. So the combination of an elastic and inertial properties generate a wave in any medium. So what is happening here is that when you oscillate the left end, you apply a force which is the tension. So the element of the string near this end will increase its length because it has some modulus. The strain will be generated because of the stress of the tension. But now this element has some tension which it will propagate further. So the element which is to the side will now experience this tension from the left end, and now its length will increase. When its length increases, it will again put a restoring force on the element which is towards its side. Now this one has a tension and its length will change. Correspondingly, this tension wave is actually traveling throughout the string, with the restoring forces pulling the string upwards and downwards. Now we are going to do a derivation to calculate the velocity of the wave in such a case. First I'm going to do a simple one with some approximations. If you are not satisfied with it, you can move to the next section where a more general derivation will be given. So over here the approximation that we are going to take is that the amplitude of oscillations is very small. So the wave does not look like this, rather it looks very smooth like this. What that means is if you take any point, the angle that the tangent makes with the horizontal is quite small. So let's say this is theta, then theta can be assumed to be small. You can see that this will not be the case when the amplitude is quite high compared to the wavelength. So if you look over here, then you can see that the angle that it makes is quite high. Another simplification this does is that the tension approximately remains constant throughout the string. In the case on the left, the tension changes rapidly. It's the least at the top points and is the maximum at the equilibrium points. We can easily take that into account, and that is what we are going to do in the next section, but for now we can simply assume that the tension is the same throughout the string. So we can forget about a wave like this. So what I'm going to do is look at a small section of this string. So I zoom in on a part over here which looks something like this. So this piece of string is being pulled from both sides. It is being pulled on the right with some tension T. It's also being pulled on the left by the same tension T. The tension is the same because of the small angle approximation. So let's say on this side the angle that it makes with the horizontal is given as theta. Because the section of the string is curving inwards, the angle that the second tension makes with the horizontal can be taken as theta minus delta theta, where delta theta is the decrease. If there were no delta theta, then this would be simply a straight line. Now of course we are going to assume that this is a differential element, and in that case delta theta would simply become d theta. We can also calculate the mass of this differential element. So if the length of this differential element is given as dx, then its mass can be calculated easily. If the mass per unit length is known, let's call it mu, then dm would be equals to mu into dx. So this is dm. As far as the inertial properties goes, we have already calculated it. Now let's see what the tension will do to this differential mass. So we can split the tension into two components. We have T sine theta minus d theta vertically upwards and T sine theta vertically downwards. In the horizontal direction we have the corresponding cosines. So you can take the net force in each direction. We are not going to look at the horizontal case because it cancels out. As we are going to see, the tensions are not the same. The horizontal component always cancels out because the part of the string only can go up or down. It is a transverse wave. So we only need to look at the vertical equation, which is T sine theta minus T sine theta minus d theta is equals to the net force in the vertical direction. Now you can evaluate this quite easily. From differentiation also you can do it, or you can expand it using trigonometry. You'll get T cos theta d theta. Because we are assuming theta is small, that would imply cos theta is approximately equal to 1. So the net force can be approximately written as T d theta. But if you apply Newton's second law, you should also be able to get the acceleration. So this is indeed the dynamics that we are talking about. T d theta is the net force should be equals to m into ay. Remember, this is the acceleration of the particle. In this case the particle being this differential section of the string. So its mass would be simply dm. From this you get T d theta is equals to mu dx into ay. But ay, as we had seen before, is given as the second partial derivative of y with respect to time, which would give us t into d theta by dx, which we take here, equals to mu into ay, which is the second partial derivative written like this. Now what we have to do is find the value of d theta by dx. To find that, let's see what theta actually means. So theta is the angle that it makes with the horizontal, which means at this point if I draw a tangent, then it will make an angle theta with the x-axis. But the slope of this curve we have already seen is given by the partial of y with respect to x. So this should be equal to tan theta. Coming back over here, we have del y by del x equals to tan theta, or differentiating this again with respect to x gives us del square y by del x square equals to secant square theta into d theta by dx, where we have applied the chain rule over here. D theta by dx is simply cosine square theta into del square y by del x square. In the small angle approximation, cosine square theta can be taken as approximately 1, which means d theta by dx can be taken as del square y by del x square, which means this equation becomes del square y by del x square into t by mu is equals to del square y by del t square. You can compare this as well. The wave equation was v square del square y by del x square equals to partial of y with respect to t. The comparison gives you the speed of the wave. From here you will get v square is equals to t by mu, or v equals to root of t by mu. This tension T is a result of the elastic property. It is a restoring force created by the spring. Mu on the other hand is due to the inertial property. We can see how both these factors came into play here. So now we can conclude by saying that the speed of a transverse wave in a string is given as root of t by mu, where t is the tension in the string and mu is the mass per unit length. Now we'll repeat the same derivation that we did with a more general approach with no approximations. So in the general case, the tension actually changes throughout the string. That is because the string has been extended by different values at different points. So imagine this is your wave. At a point near the peak, the string element here is hardly extended. But for a point which is over here, the string element has been extended by a huge amount. So since the strain is higher, the stress will also be higher. So we'll do the same thing again. Let's look at this differential element. There are forces which are pulling it from both sides, but let's call these forces now T1 and T2. So T1 is the force by which the element on the left pulls our differential element, and T2 is the force by which the element on the right pulls it. So let's make the free body diagram again. We have T2, which is acting at an angle of theta minus d theta, and we have T1, which is acting at an angle greater than that, which is theta. Now since we know that our differential element cannot move horizontally, it can only move vertically, the horizontal component should cancel out, which means T2 cos theta minus d theta should be equals to T1 cos theta. So this should give you some indication. As the value of theta decreases, the value of the tension should also decrease, justifying our earlier proposition, that is, as the angle keeps on getting more steeper, the tension also increases. So we can also look at an element which is right beside our main element over here. It will be pulled to the left with this tension T2 at an angle of theta minus d theta, and it will be pulled to the right with some tension T3 with an angle theta minus 2d theta. The condition again will apply. You will have T3 cos theta minus 2d theta is equals to T2 cos theta minus d theta. From this and over here you should get the general idea. The tension at any point of the string given as t theta multiplied by cosine of that angle theta that it makes with the horizontal should be equals to constant, since all of them equate to the same value. You can find that constant by putting theta equals to 0. Let's call that tension simply T. This is the tension when theta equals to 0, so this is at the peak of the wave, the tension at this point, and the tension at any other point given by this equation T theta cos theta equals to T. Now we are in a position to write the vertical net force as well. So the vertical components give us T1 sine theta minus T2 sine theta minus d theta equals to F net. Now you can use this equation over here. If you do the simplification, you will obtain T1 into d theta upon cosine of theta. This should be equals to ma, so dm into del square y by del t square. Dm as before is given as mu dx, which means this will become T1 upon cosine theta into d theta by dx equals to mu del square y by del t square. Now if you recall, we got this value by finding the slope del y by del x and differentiating it again to get d theta by dx as simply cos square theta multiplied by del square y by del x square. So you can put that over here and you will get T1 into cos square theta upon cos theta equals to mu del square y by del t square. This gives you T1 cos theta, but we already know that T1 cos theta is equals to the tension at the top when theta is equals to 0. So this gives us T del square y by del x square equals to del square y by del t square, which gives us the same result, with the tension T now being the tension at the top, which is also the tension which would be maintained if you did not produce any wave and were just stretching the string. That is when the entire string is theta equals to 0. So you keep the string like this, you pull it with some tension T. That is the value here. So by now you should be convinced that indeed the speed of the transverse wave in a string is given as root of T by mu. Now we are going to see how much energy or power is being transmitted as the wave moves from one place to other. So once again we are going to look at a single section of this string. It's being pulled on both sides by the tension T, and we are going to assume that the theta is small. Theta is the angle with the x-axis as was mentioned before. We have to find how much work or how much power is being delivered by the force on the left. So this tension is acting in this direction and does some work on this. So the power is given by the force and the dot product of it with the velocity. So this particle has a velocity which is upwards and the force is in this direction. So what we have to do is simply find the component of the force along the velocity, which means the vertical direction. That will be nothing but minus T sine theta. In the approximation theta is small, this will also be minus T tan theta. The reason we write tan theta is because we have seen before tan theta is simply the partial derivative of y with respect to x. Also the velocity is known. Particle velocity is given as del y by del t. So the power delivered by the force on the left hand side is simply minus T del y by del x into del y by del t. So indeed what happens in a wave is that power is being delivered from each section of the string onto the other section and the transmission takes place. So first this part of the string transfers some energy to this part, then this part of the string transfers the energy to the next part, and so on. That's how the energy from your hand or whatever is driving the wave travels throughout the string. The energy transmitted per unit time is the power is given by this formula. Now if you want, you can calculate this specifically for a sinusoidal wave, which means y is given as a sine of kx minus omega t. Forget about the phase constant for now, which means del y by del x equals to ka cos kx minus omega t, and del y by del t is equals to omega a cos kx minus omega t. Substitute both of these over here and you get power transmitted is minus t a square k omega cos square kx minus omega t. Now if you want, you can recast this into other forms by taking the wave number k as simply omega by v, this becomes P equals to minus T A square omega square by V, where this V is the wave speed, not the particle speed, into cosine square kx minus omega t. Also you can replace the tension T. So we know that the wave speed V is equals to root of T by mu, which means T is equals to V square into mu. Putting that over here gives us the power transmitted is equals to minus mu V A square omega square cosine square kx minus omega t. So you can see that because of this cosine square term, this power transmitted changes with x and with time. So it's different for different points, but we can take an average over an entire interval, and that would give us the average power. Now I'm going to do a derivation which is very important and will be used again and again whenever we are trying to calculate averages of sinusoidal waves. My objective is to find the average of this power, and for that I need to find the average of the cosine square function. So what I'm going to do is develop a method of finding the averages of continuous functions. So let's take a detour to mathematics. A function is given, let's say sin x, and you have to find its average from, let's say, 0 to pi by 2. It takes on different values, but you can calculate its average. In statistics, the average is defined as taking the sum over all the discrete values and then dividing by the number of values that you take. Now for a continuous function, what this will do is you'll have to take the sum over all points between 0 and pi by 2 and add up their signs and divide by the number of points. But since there are infinite number of points, we do not need to take the sum, rather we are going to do a definite integral. So we divide it into small intervals, each of which dx. The summation then becomes the integral of sin x dx as x goes from 0 to pi by 2 divided by the total interval itself. So in this case it would simply become integral of dx from 0 to pi by 2. This is a general formula to find the average of any function, which is the average f bar x is equals to integral of fx dx over the required interval, let's say from a to b, divided by dx from a to b. This denominator is simply b minus a. So I hope you get the idea. Now you have to calculate the average of the function cosine square kx minus omega t over an entire cycle. An entire cycle is of 2 pi. So forget about kx and omega t. Let's find the average of the function cosine square theta as theta goes from 0 to 2 pi over an entire interval. We also have to divide it by the length of the interval, which is 2 pi. Now you can do this integration yourself. What you can do is put cosine square theta as 1 plus cos 2 theta by 2 and then integrate both of them. You will find out that when you evaluate this comes out to be 1 by 2. And that's not it. It has more interesting properties as well. You will find out that taking the average of cos square theta from 0 to pi by 2 also gives you the same result, which is 1/2, or from pi by 2 to pi, or from 0 to pi. So if you take the average in any of the quadrants, you always get 1/2. Similarly for sin square theta, if you take the average in any quadrant from 0 to 2 pi, 0 to pi, or 0 to pi by 2, you will get 1/2. So make sure to remember this result. Also, as an alternative exercise, find the average of the function sin theta from 0 to pi or from 0 to 2 pi and see if you get what you expect. So now coming back to our power, the average of the cosine square function here will be 1/2. Everything else is a constant, so the power becomes as 1 by 2 mu v a square omega square. This is the power transmitted in a traveling wave. It's important to make the distinction because later on we are going to encounter standing waves as well. So you don't have to remember all these formulas. What you have to remember is the following: that the power is proportional to the square of the amplitude and it's proportional to the square of the frequency. Now this first result is actually quite general, and we'll see later on that the intensity of waves is also proportional to the square of the amplitude, intensity of sound waves, intensity of light waves, and so on. But its origins lies over here. Also, the square of the frequency should become clear. Which means for the same amplitude, if we double the frequency, the power becomes 4 times.